Awesome. Welcome, everybody. This is the LeetCode study group. We've done two sessions before this. The first one was 2-pointers and sliding windows was the second one. Now we're on the third session. And this is some of our team members, Chethana and Karen. And we have Janani who's joined us this time. Last time Soumya joined in. So all four of us, we're part of the LeetCode study group. So let's start off with today's agenda. Janani had posted a guessing kind of game in the LeetCode study group channel. So let's talk a little bit about it. And then we can dive into binary search, and then we could talk about the problem we're discussing today, along with some test cases and how we can what the time complexity is, and code that out. Then we'll next talk about what the next problems may be for you to tackle, and then we'll end it with a round of Q&A. Okay, so before I continue, today we're going to do a lot of like scratchpad stuff in REPL. Like we're going to do like a lot of visualizing within REPL. So let's just jump right in. Okay, so we were also talking about the guessing game, right? So for those who didn't see that message, we'll recap that again and some of it again. And then we'll okay, so if you're if you can see my screen okay, put in a thumbs up in the chat for the REPL page, and like if the font is okay and everything, just let me know. Awesome. Okay, so the guessing game, right? So we have a list of integers from 1 to n, and there are no duplicates. We're assuming there are no duplicates because it's our problem. We can assume our own conditions. So, is everybody able to see me okay? I mean, see the screen okay? Like, I'm gonna zoom in just in case. We'll see, like if it's already okay. Yeah, is it okay now? Okay, fine. Great. So you have a list of integers from 1 to n, and then you'll have to guess the number I've picked, which is let's call it target. Okay. So if you find that target, then you return the target. Otherwise, you return -1. Okay. So how do we find this target index in the simplest, like the most brute force way possible? Let's not call it brute force because it seems a bit too, problem solving initially itself. So let's see how we can find the number that I've picked in an easy way. Okay, so you would just basically, it would be like this guessing game where like I could, you would ask me, oh, is 1 the number you've picked? Okay, let's actually do that with an example, right? So if your n is 10, you'll start from 1 to 10, right? So you'll ask me, and if the target is 9, the first time the target is 9, let's start this process that we're thinking about. So if you'll start by asking me, is 1 the number you picked? Is 2 the number you picked? Is 3 the number you picked? Is 4, 5, 6, 7, 8, 9? Once you hit 9, and I'll say, okay, fine, you win. You've been asking me way too many times, like you win. And then I'll sort of, go with it. So what we've done here essentially is a linear search across the array. And then we've, the difference here from what was posted on the channel to here is that we're trying to return an index, right? So once you hit 9, you'll return 8, basically, if we're doing it in a like search for this thing and then return its index. If you don't find it, you return -1. So that's the linear search approach that we're sort of like doing here. Okay, so again, like we're doing one by one, we'll do like this kind of check where we're like, okay, 1 is 1 equal to your target? No, 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 and like so on. So yeah, for the first one, the output is 8 because that's the index. These are the indices. I sort of like pre-wrote them already. So yeah, and then now we're gonna look for 30, and then we're gonna check now, right? So now we're like, obviously, the 30 is not present in this entire array, and you'll probably know about that only when you hit the end of the array. Here I've presented like a very neat sequence where there's no like bumps or anything. So in the real world, it's probably not going to be the same. So yeah. Okay, so we don't have 30 in our array, so we're returning -1. That's the output. Okay, so so far so good, right? Like we're just looking for something, we're checking one by one and then returning. Suppose our n is 100,000. It's obviously going to be like millions and millions, like, you know, in real world data. So if our n is this, should we use the same approach? Maybe our target is 1,000, or, you know, like the target is not even like, you know, it's you have to look through the entire array to figure out that the target is not present in your array. In that case, like, you know, what happens? Like, I sort of want to ask you a general question. So what do you think? I think it's fairly, because we've done these kinds of problems before, it's fairly okay to judge what the time complexity is. So what do you think the time complexity of this is in the worst case possible? Drop it down in the chat if possible. Okay. Great. So yeah, O of n. Yeah, where n is the length of the array that we have. And space is like, it depends, right? Like here we're not using any space. We're just doing a lot of computations that may probably not be needed. Okay, what is one more thing we're noticing about this this array? If possible, drop it in chat. We'll discuss it later in detail, but for now, okay. Good. Yeah, it's a very neat kind of like array that we have. Okay. So we've just like spoken about, you know, how we can avoid unnecessary kinds of computations. Let's see, can we do better, you know, from what we currently have? Yes, we can. And we're going to see how. That's called that algorithm that we're going to look at. The search algorithm that we're going to look at is binary search. Let's jump back to the slides. Great. Okay, so binary search. What is it, right? Let's just define it here, and then we'll get into it in depth when we look at an example. So you perform, it's a search, so you perform a search, and it is different from linear search in that in linear search you visit every element, and every single element within the array. You don't have to, because of one of the conditions you dropped on the chat. So let's discuss a little bit more. So you're going to reduce the search space, and like when I say search space, like it's if it's an array, it's an array, so and so on. So like you're going to reduce it by half every time until you get to that last element. Or, you know, if you may find your target or your search condition may stop before you get to that last element or last one element, but you're essentially drilling down to the end. But yeah, if you don't find your whatever condition, or like if you don't find your target within that till you hit that last element, then probably it's not present in your input array. Okay. So once you hit that last element, your algorithm stops. So like initially, like what does this, do you is there like, if you're looking at it for the first time, sometimes you may feel like, wait, this seems like some kind of two-pointer kind of thing or something like that. Like, are you able to like discern the difference between two pointers and binary search, in that they can sometimes be different, they can sometimes be used like in correlation with others? So like what is the difference between that and this according to you? You don't have to like, it doesn't have to be like a long answer, but do you see any kind of difference? Drop it in chat if so. Okay. Yeah, so there's pretty much like you can use two pointers with like a binary search, but essentially in like a, yeah, okay, time complexity wise, okay. So in a binary search, you sort of like, you sort of remove out a portion of the search space. You keep going from like a large section to like you drill down to like one, and like sometimes that can also be used with the normal two-pointer approach as well. So yeah, it's a very weird kind of thing, because like I always like, anytime I do binary search, I have this thing where, wait, like why do I think it's similar to two pointers? And like it may be, it may not be. So yeah, just wanted to talk about that. Okay, so we've discussed, something, like we've spoken about some that it sort of shrinks down and stuff, but how does it work? For this, let's just go back. Okay, so here I've already written down like the binary search, like the template. You'd basically like I'll explain to you as we do this. I am thinking of reducing the font for this to the previous one, just for this, because I want to show you like side by side. So do you think we can reduce it a little bit? Okay, let's do that. So yeah, it's just for, I just want to be able to show you the algorithm here, and also like the same example that we did before, basically. Okay. So in general, for a binary search, you need a couple of things. Okay. We're going to first go through this, and then we're going to talk about the sorting condition that we spoke about before. But that thing is very, very important. Your input should be sorted in some kind of order. It could be ascending, descending, like topological. There are many kinds of sortings out there. So it has to be, if it's an array, it has to be like, any kind of order. Okay. And then we'll discuss like the next condition after that. Okay. So let's say we have the same array from before, and here we're doing like a, let's move you up. Okay. Let's move up further. Okay, perfect. Yeah, so we have the same array from before, and then we have like the indices and everything marked down, and then it's the same problem. You just have to like, you have a bunch of numbers. You have to find out the target within those numbers, and then your input is sorted. So yeah. Okay, like we have to, the first round, our target is equal to 9. Let's try to find 9 within this array using binary search. Before we did it one by one. Now we're going to do it the same using binary search. Okay, we have, great. Let's just move our two like start and end limits to like, or pointers to the start and end of the array. We need that because now we're going to, initially we find out the start and end. Now we're going to find out for every, until you hit your condition or until you hit a point where your start pointer is greater than your end pointer, like this, like, I don't know why I'm showing it that way, but until it hits that kind of condition, you're going to keep going. If it hits that condition, you know that the element that you're looking for is not within the array, and then you're returning -1 here. Okay, so let's see here, right? So our mid initially, so for now, let's start with 0 and, our end is 10. And then let's keep all of this empty because we'll fill it out as we go on. Okay, so you have like 0 plus 9 divided by 2, and this kind of division, if it sort of rounds it down to, it doesn't round it up, it rounds it down. So 9 by 2 is 4. So our mid would be, our mid index is going to be 4 that you'd put in here, and then your element that's actually at the mid index is 5. Okay, so next, okay, before we continue, like, everybody doing okay? Like, you want to drop in any kinds of cues for me, like a thumbs up or something? Good, awesome. Okay, so now our mid is 5. The element at mid is 5, and our target is 9. Now we'll check here. Is 5 equal to 9? No. Is 5 lesser than 9? Yes. So if that is the case, then you take the start pointer. You will sort of, because your mid was here, right? I did that, sorry. Your mid was here. So you'll sort of take your start pointer and you'll move it all the way, leave out all of this, you'll move it all the way here. So I'm going to use the mid as a start. So essentially your start pointer will move to here, and you would not have even processed all of these elements, and you don't need to because it's sorted, and you know for sure that like 9 is not going to be to the left side of your mid because and now we're here, right? Great. So again, we have to compute the mid here. So 9 plus 5 is 14. Also, you sort of have to update your start pointer. You'll sort of go along with this, right? You'll basically keep going. You'll find the mid, you'll keep comparing, and you'll keep moving your start or end pointers. Great. So our start is going to be at 5, and then our end is the same because we've not really moved it. And then our mid is going to be 1 second. Okay, so so it's going to be so 15 by 2 is 7. So this is going to be our mid, which is here, and then okay, this we're here now, right? We found out 7, and then array of mid is 8, which is here, and now we're going to check our condition, right? If your array of mid is equal to target, is 8 equal to 9? No. Is 8 lesser than 9? Yes. So now you'd again move your start pointer to mid plus 1. So it would be over, where was that before? Oops. Yeah. So it would be over here. So it'll be like 9 and 10 would be like your, I'm not able to do this properly. Let's see if I can type properly. Okay, so this is going to be your start, end. Currently your start is going to be at 8, and then you'll find mid, right? Ooh, why did I? Oh, did I? Yeah, I probably did. I'm so sorry. It should have been length of the array minus 1. Put it in as 10. Okay. So, okay, fine. I think if this is the case, then I'm going to do this again. So sorry. Yeah, it should be essentially, I think you get the gist though. Like it has to be every single time you're going to update either your start or your end. And how are you going to do it? You're going to either move it to you're going to base it on mid because you can skip one whole portion of the array, and you can sort of like lessen your space until you get to that one, or like your condition is satisfied. So something like that. That's what we're doing here. And if you noticed, like if you get to, you will eventually you will get to this point. Your mid will be at this point. I think it's right at this step, but because I messed up the numbering there, it probably didn't pan out well. But you will end up at this point where your start and your mid would point to 9, like according to this example. And then when once you hit this point, you'll again start to check, like if your array of mid would be here, and then if that's equal to target, and then you'd return mid, which is 8, which is your output. Okay, so in this entire process, we noticed that a lot of these things are like a lot of, yeah, so we're returning the index, so that's 8, which is what we're doing here as well. We're returning the index of where we find our target within the array. Does that sound okay? If you have any more questions, like just drop it in the chat and we'll we'll go through it. Okay. Oh yeah, yeah. Yeah, I'll okay, yeah. It's the index. I thought like there's somewhere we missed that. Sorry about that. Okay, so at the end of all of this, in this example, you'll return 8, because that's where your target is. Otherwise, if in another scenario or something like that, you'll return a -1. Oh, okay. A lot of like this is super similar to like many of the things we've seen before. There's just like slight nuances within it. Okay. Yeah. So now let's just go back. So now we sort of saw how it works, and this whole thing is present. Like this is all within the REPL, so you can check it out anytime you want, and play around with it, or like fork it and play around with it. Yeah. So let's get back to our slides. So we saw that there are a couple of conditions of when we should actually use binary search. So like the first one is that the input should be sorted in some kind of order, and then the order in which that input is sorted, it should be compatible with your search algorithm. Sometimes it may be ascending, or like descending, or like there's like all of those things. And if you have like for example this kind of input, right, like -1, 6, 7, 10, 15, this is sorted in ascending order. So your algorithm, you would, if there's any kind of number that is like maybe lesser than your mid on the right side, then you know that you can't use binary search, or you should sort it in some kind of way. Yeah. So the same thing goes with like descending. It should be like, because this is descending, then your entire array should depend on the fact that anything that is to the left of the current element is going to be greater. If you see anything lesser, then no, it's a definite no. Okay. one more question that I thought of dropping in for you. What kind of, because we've seen some kinds of stuff pertaining to binary search, uh, and an example problem sort of. So like what kind of problems do you think we can use this in? Like what kind of, um, for example, like, like would we use this in, yeah, I'm not thinking of an example, but like, what do you think would be the use case of this? Which kinds of problems, if you see it, you would know, oh, okay, this maybe I should try to do a binary search here so far from what we've discussed. If you have any kinds of, that's a, yeah, the phone book is yeah, it's a classic example of binary search. Awesome. Yeah, yeah. Like, like because it would be ordered in some kind of way, and then you can just eliminate. You don't have to go through every single like entry in that phone book. You would sort of look based on read may lie. Student records, yes, yes. Card catalog, yep, yep. Nice, nice. Really like this. Yeah, so even within like in terms of LeetCode, it may be like when you see, like just like a general template for you to like be like, oh, okay, binary search. So if there's some kind of like a, um hash table with, yeah, it's like a, yeah, hash tables have a constant lookup, and yeah, I'll have to think about that. I think so, yeah. But like it should be ordered, right? Hmm. Searching for your name in the phone book, yeah. Awesome, awesome. So in terms of LeetCode, the one thing that I have noticed is like, be like find something within this sorted something, Yeah, perfect. Yeah. Just like find and like some kind of ordering that's given. So that would be like classic, like if you basically do like binary search, LeetCode problem types or binary search problem types or something in Google, or like just search for it online, you'll just like literally the ones I've seen before, and everything would have the same thing, like, like you have to find something and then within this, sort of sorted array. Okay, like let's move on. Okay, so this is a very yeah, yeah, you could do that, but like, again, sorting would also do like an n log n. Sometimes, in problems specifically, like, um like sometimes it may be like do this in like log n or something like that. But yeah, but anything is better than exponential time. So yeah, definitely. Yeah, so let's talk about the time complexity here. It's a very like, if you see anybody say like, can you solve this in of log n with the same constraint from before, the first thing you would do is that you'd worry about, oh, okay, like, I think I'm gonna probably binary search here. So it's one of those kinds of problems. It's super like patterns or algorithms, super powerful. I'm gonna call it a pattern in because it's one of those like algorithms that's like that has a lot of use cases within problem solving as well. Okay, so let's talk about the time complexity. And like the reason I pre-wrote a lot of this stuff is because like when we explain, and like the flow that we usually have while preparing and stuff, like I wanted to like pass that on while we do the session. So yeah. Okay, so let's do the same n equals 10, the same thing. You've probably gotten bored of this example by now, but if you haven't, let's talk. So if you notice the halving, or like it always like reduces by half, if you notice, because we're doing like, like start plus n by 2, like to find the midpoint. So initially was 10, and then you halved it, and it became, you sort of removed all of this in the search space, and then you got to this, and then from here you did it again. The when I say n, it's the initial n. So 10 by 10 by 2, 10 by 4, and then we got to this kind of thing, and then finally once we hit this, it would be like, okay, we've sort of figured out the target, and then that's it, like, you'd return. So this would, it's mostly like, how many times do you divide that search space, how many times do you divide it by 2 to get it to 1, that last one element. That's the last thing you'd be left with. Here we figured out our target before we hit that condition till the end, but like, yeah, you'd get that one element, and how many times do you have to divide to get to that. So mathematically, or just it's very, like, there's a much more like math based kind of explanation. Like, there are many more for binary search. Like, I've linked one here. Like, it's by Gaurav Sen. Like, he does a lot of computer science algorithm stuff, explanations. So, and he does it with proofs and stuff. So you should definitely check it out if you're doing it. So yeah. So this, let's talk about what we've written here. We have the n, our search space, and then that divided by, if we're going to, so n by 4 is n divided by 2 square, right? And so on. And this is, if it were bigger, it would, yeah, I'll do this as well. N divided by 2 power 1, and then n divided by 2 square, and that's how we keep going till we get 1. So yeah, so this is like, if you sort of like normalize it, it would be 2 power x, where x is like the exponent that we're seeing here, and you should sort of bring that to 1, the last step, 1. So now, like, if we sort of like cross multiply, it would be like n equals, this goes over to that side, n equals 2 power x, and then to find, now we have to find x, and by like logarithmic properties, we're doing binary log, here. So like, if we apply log on both sides, it's in the end, you're going to like, yeah, if you apply log on both sides, you'll have like, x log n equals x log 2, like to the base 2 for both, and then this log 2 base 2, that would return 1. So and then you'd literally find out that x equals log n. That would be like the time complexity for binary search. There are surely a lot of like resources that do that get into the math even more than what I've described here. So definitely check them out. I think for the context of how this would go, you should just remember that every time the search space reduces by half, and how do we get to that 1? And like, when you think of those things, it would sort of click, and you get to that equation, and then you could just get to log n after that. So that is the time complexity kind of thing that I wanted to talk about for binary search with like with respect to what we have here. Awesome. So okay, before we get into the problem, I'm going to take a quick water break. If anybody has any questions or anything, please drop it in the chat, and we'll get to them definitely.
Thank you, Chethana. So I'm gonna post the GitHub link for you guys to access the material. Meanwhile, give me a second. I had it open, but I closed it. Let's see. There we go. Meanwhile, big shout out to Janani for the easy problem introduction. It was very easy to understand. It's actually really great to introduce the binary search. Great job,
Yeah,
great job.
yeah.
Kudos to you.
Awesome job, Janani. Like, I think that sort of like introduce everybody to, like understand binary search better. Yeah.
Hope everyone understands. So feel free to try. We will be posting more easy problem there. So if you're not familiar with particular topics, like feel free to try out the easy problem plus, and then if you have any questions, like feel free to ask us or post it there, share your thoughts, like see, oh, this is right or wrong, and uh, yeah, that would be the great way to we learn from each other.
Yeah. Yeah. Awesome. 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 Okay. So is everybody ready to get into the problem? Drop me a B or a thumbs up. Awesome. Awesome. Great. Great. That is awesome, everybody. Thank you so much for the support there. Um, Great. So let's talk about the problem that we're actually going to do. It's called search in rotated sorted array on LeetCode, and as always, it'll be linked to this, like to the words. Sorry, I'm not able to get the words out. Anyway, let's read through what this actually means, and then we'll see like how to actually do this. So there is an integer array nums. I've literally lifted it off of like LeetCode onto here so that we'll just see how to like break it down as always. So there's an integer array nums sorted in ascending order with distinct values. So Janani was like, when we were discussing before, she mentioned like she came up with this question actually. So what do you think is yeah, words are hard sometimes. Yeah. So what do you think is the difference between non-decreasing order versus ascending order? Um, it was very different kind of question. So like what do you think is the difference? Drop it down in the chat so that we can read together. Hmm. Yep. Yeah. So when you say specifically like ascending, strictly increasing, so that's there. If you say non-decreasing, it's a bit of a caveat. It's like a loophole, like, oh, so if it's non-decreasing, can it also be equal? So like there you will have uh elements on there that will be equal, but they will also satisfy the thing where they don't decrease as they go on, so it'll be equal or greater. So that's the difference between non-decreasing and ascending. So this is ascending, thankfully, and then we this time we have like we're going to work with distinct values, like because it's ascending, it cannot be equal, therefore like it cannot be, if it's equal it won't be strictly increasing, and yeah. So okay, so prior to being passed to your function, nums is possibly rotated at an unknown pivot index k. I'll explain that in the next slide. But for now, we'll just know that your input has been tampered with before it got to you. It's been rotated once at that pivot index. At that particular index, you'll know later on. So given the array, given nums, after the possible rotation, so like given the rotated sorted array nums and an integer target, you should return the index of target if it is in nums, or -1 if it's not in nums. So this part is fine. If the question was just this, we would all know to do it, definitely. But then the rotation makes it a little bit weird. So we'll talk about that in a second. Right. So how do you simplify this question, right? We're given an integer array, nums, and then nums is sorted in ascending order, and it does not have any duplicates. And then we also discuss that thing where it's rotated. So how is it rotated? So this is not the input that we'd be given. The second one's the input we would be given, but before it reaches, we get to that rotated part of it, this is how it would have been. And if k is the index where the is the pivot where the rotation happens, it's like if k equals 3, so that'd be like 0, 1, 2, 3. So 3 is here, and then everything before that would sort of go to the end. So if you have 4, 5, 6, 7, 0, 1, 2, it's almost the same array, but then it's like you have two different sorted kinds of arrays, sub arrays within the main array. And then that is what the rotation means in this sense. Given target, find the index of target in the rotated array nums. Okay, so if this particular target is present, then you'd return that target index. Otherwise, you would return -1. So, okay, as always, edge cases. Let's talk about edge cases. Is there any according to, I'm basically this time we're going to strictly follow what we had seen there, because it's already sorted and they do not say you have duplicates, and it's only rotated at one pivot, like it's rotated based on that. So we know those three things. And can it be empty? Usually we go through these questions, right? What other kinds of questions can we ask? They're saying integer array, right? So yeah. So is it both positive and negative? Yes, no. Yeah, it's probably both, right? So I guess is there any other kind of edge cases we're thinking about? I think this problem has been pretty laid down. I feel like the conditions and stuff, we sort of know where we're going because it's already in the problem statement. Yeah. So that is possible too. If it was at the index, then definitely it would look like there's no shift at all. It would just be the original array. For this example that I chose k equals 3. If it was k equals 0, then literally you don't have anything to rotate over there. Everything would be literally the same. Yeah. And that is also possible. Yeah. Okay, so do you think we can go ahead and get started with the problem? Drop me a B or a thumbs up if possible in the chat. Very cool, very cool. Okay, let's go. So let's go back to our our problem. Okay, so we've so far I've just written this part out. I just wrote out the couple of examples that we have, right? So if you're given your nums is this, and then your target is maybe 0, then your index, it would be 0, 1, 2, 3, 4. So target, like the output would be 4. And we would sort of like, the weird thing about this problem is that we always keep thinking, oh, it would be great if it was like, if it was um, sorted beforehand, and stuff like that. Yeah. So there was another thing that was mentioned in the problem. This has to be like, it has to be solved in O of log n. Like otherwise, I think it would time out in LeetCode. But we are going to discuss in general what other kinds of things that we can do. I don't know why I wrote this down. Probably I'll change that. Okay. So if your nums is 0, 1, -1, and then your target is -1, it would be 0, 1, 2, right? So that would be your output. Okay. So let's talk approaches, shall we? So the first one is a brute force. Okay. What do you think is the brute force for this? We've discussed this from the, I probably may not do as much of like a detailed discussion like on exactly binary search now, because like we've discussed a little bit, we've discussed the algorithm before. So I may go slightly faster, but if you feel like it's too fast, let me know. I'll like slow it down. So what is the brute force here? If you have any kind of idea. You could still like I think we could also do like we're just checking if target is present in nums, right? Like just generally. So it could also still be an O of log n, O of n kind of brute force, right? If we're just going to look, yeah. No worries, no worries. Yeah, that is great. So linear search, let's write it down because we're getting to this point. So linear search, and this would be like we said, our time complexity here would be O of n, and I don't think we're going to have any. No, we're not going to have any kind of like like space situations here. So we're just going to store anything. So that's constant space. Okay. Next one would be, I mean, if you could also like, we could also do that thing that algorithm that Joanne mentioned. We could like sort it, and then like it would be, because the sorting comes into play, sort and then search. That would be like an log n, because we're the fastest sorting algorithm is in that range. Okay. And then time wise, like we know that yeah, that's good, like we're getting there. Yeah. So the third one would be so the third one would be like because we know that there's only one point where the rotation happens, so we just need to find out like the point where we just need to sort of move our starting pointer, or like the pointer which is initially here. Like this would be, if we're doing it this way, this would be like the first, like the starting of the array, right? And then this would be at the end, I guess. Yeah. So so like we have to somehow move this to get to this, and then we could do like an offset. We could find like another like offset to actually get to the midpoint. Like if you move your start position to this, and then you sort of think like, okay, my start pointer is over here, and then now we're going to have to find like another, like a full array kind of mid. Like you're going to pretend that it's sorted completely, but you're going to get to this pivot point or this other kind of start pointer thing. Like you're going to find that first using binary search, and then you're going to do another binary search on the same array, and you're going to get to your target. So it goes like this, right? Like let's first write it down, and then we'll think about it. We'll think about how to do it. So far, what do we know? We know that there is one giant array, but then it has two pieces of sorted subarrays within it. So if we figure out where the start of that actual, the actual array before it was rotated is, then we can do like another, we can assume that that is the start, and whatever is the end would be the end, and then we can sort of get to where we can find the midpoint, and then we could do like another binary search on it. It's a little bit difficult when we talk about it. Like I'll explain as we code and stuff like that. So we have these kinds of conditions, and first we need to find that rotated pivot index position. Okay, and then once that's done, we'll do a binary search with the rest of it, like with the rest of the with the array again, to find your target. So if you think of this is probably like a log n plus a log n y, because we're finding this using binary search, and then this would be another log n, because we're going to sort of do the actual binary search. But then there will be like the slight modification with the midpoint that I'll mention it to you as we go on. So this, at the end, this is just going to be log n, because it's not looped within it or anything like that. So yeah. So what we're going to do is that we'll sort of like move our start pointer or our left pointer towards that ideal index, and then we'll sort of like assign it over, like we'll call it pivot or something, and then we'll do the whole we could sort of do like the whole, like the entire binary search on the entire array again. We'll move back our start and end pointers, and then we could do like a binary search. But then we'll need to find like another mid. We'll have a mid already for it, but then we'll need to find another mid based on based on the pivot that we have. And then you'll offset it. I'll show you while we code. But yeah. So it'll be like a mid. You'll have the mid, and then you'll have the pivot, and then you'll offset it. You'll do like a modulo based on n, and then you'll get to this other midpoint, which is where you will look. You will search. It's how you'll search. Like I think as we go on, we'll sort of get there. So do you think we can maybe we can, and as far as the space complexity goes, I don't think we're really using anything, so it's constant space. This is just the time. I'll write this out better like after the session is over, so that we sort of understand. Yeah, okay, so one more water break. Thank you for bearing with me and my squeaky bottle. Let's start coding it up. Okay. So initially, let's have this. Let's already have like our variables declared. Let's just keep track of our the length of nums, and then we're going to do like a here we'll just do like a start, and then and then your end would be n minus 1. And now like you could call them left, you could call them right, like like you could go that way. I like to use these in general for like pointers. So yeah, it's just my opinion, but yeah. So now we need to we need to find our pivot. Okay, weird. Okay, we need to find our pivot, and for that we'll move our start pointer to to where it actually should have been. So to like the rotation index. So yeah, let's first do that, right? So if you have any kinds of like questions as we go on, let me know. I'll try my best to like make this as quick and like easy to understand as possible. Okay, so let's loop over, right? Why are we going to like we need to move, we need to keep moving until we hit that point where it's like, oh wait, like some kind of number, because this is supposed to be ascending order. So if we have a mid that is like that's like lesser than, like if your mid like if you're I think like if your mid element is like, how do I say this? Yeah, sort of getting brain freezes. But if your mid number is greater than your maybe like the number towards the entire right, then that means that it's not possible, right? If it's in ascending order, it has to be everything to the left has to be lesser, everything to the right has to be greater. But if you see an element to the right that is lesser than your mid, then that means that you still have not found your pivot and or your rotation index, or where the original like index, the original array index should have been, like the start of the array. So you will move closer towards the right in that case. Okay. Otherwise, what you do is, that means if everything's okay, that means you'll keep moving your end pointer closer to your start pointer. So let's do it like this. So while your start is lesser than equal to end, because that's your initial condition. Let's do mid, right? We have to find out the midpoint, and then we have to like do the comparison like we mentioned. So that would be start plus end divided by 2, and then if your nums of start is, sorry, if your nums of mid, what's wrong with me? Okay. If it is greater than nums of end, then we see this situation where we have to move towards, we still have to keep moving towards the right. So in that case, you would move your start pointer closer, like you do mid plus 1, because you'd have to remove, or you don't have to see everything else there. So your start pointer would be mid plus 1. Otherwise, your end pointer would be equal to mid, because that's that if in case where like your nums of mid is like lesser than lesser than the end, that means you still have to keep moving towards the left. So like, yeah. Okay, so once this is done, it would at this point it would be like your start pointer at the end of this whole iteration, your start pointer would be exactly where the rotation sort of happened. So we're going to be moving our start pointer, we're going to be renaming our we're going to be assigning that to pivot so that we sort of this is needed because we need to figure out how to do the mid, how to offset the mid later on in the problem. So yeah, so your pivot is going to be your start. And then next, what we do is, this is actually our kind of like our binary search portion where we do where we look to see if our target is present in nums, and if it isn't, you just return a -1. And we didn't take care of like the if it's empty or anything, because we sort of like there's at least like one element in nums. Also take have a check that's like, if the length of nums is 1, and like if it's not equal to target, you return -1 immediately. You could do that right at the start. But yeah, so okay, so now let's reassign, right? Let's back our start and our end. I think the end will like depending on, like for our example, the end just stayed at the end, but sometimes like, it depends, like, yeah. So we're gonna assign our end to n-1 again. Now we're going to go over like the same binary search, but then we're going to find like another mid to our previous mid for the offsetting portion, because this is not a normal binary search in this case, because we're doing like this is our pivot, this is our start, and this is, like this would be our end at this point. So okay, so while start, the same thing, you start is lesser than or equal to your end, you'll find the mid, right? Mid would be start plus end divided by 2. Okay, and now it's like, it's this part is like super interesting, because like this is where we're doing the actual like, you can't just do it like this and then continue, right? Because the mid would be it would need to take into account the pivot as well, because wherever the pivot is, that is the actual start of the array. So let's call this mid, yeah, second mid, I don't know, second mid. So that would be like you would take the, so that would be like you take the current mid, and then you will add in your pivot to it, and then you will offset that, like you will do a modulo by n, where n is the length of your nums. And once this is done, this would sort of ensure you're like this isn't like the normal binary search that we have, because we're gonna like this, it would start with like 0 1. You need to take care of that part of it. Once this is done, we'll just do like the usual. This one will point to the mid that we want. So it'll be like if if your nums of your second mid, if that is equal to your target, then you'd basically return second mid. Else if your, yeah, the usual binary term, binary search stuff. So if your nums of this, yeah. So it's like a binary search, like it's like binary search within binary search, but not like nested. It's like because we're doing the mid calculation again. So this is just because the input is not, it's not in the right way. So yeah. Yeah, so if this is like lesser than this is lesser than your target, then you would move your start pointer to +1, and then it's this part is pretty much intuitive, like the usual stuff. And then once this is done, you will at the end of it all, you'll return you should have returned mid here, but if you didn't, you'd return a -1 at the end. Yeah. Okay, so far so good. I think we've sort of come to the portion where there's so many different ways of doing this. One of my other favorite ways is where yeah, so like so if you do mid plus where is your mid? I think we can do it with an example or something. Sorry about like very less sleep, so yeah. So yeah, so if we have like okay, so if we're doing our initial, this is going to be our pivot, right? This is going to be our pivot, and then this would be our start, and then this would be our end. Here it would be like a for the first one, you would do mid, like, yeah. If you're starting initially over here at 0 plus, how much is that? 0, 1, 2, 3, 6, 7, right? So it would be, yeah, it would be 7 by 2. 7 by 2 is 3. 3 would be your mid here. Where am I? Yeah. 3 would be your mid here. And then over here, it would be like 3 plus, what is your pivot from here? It is 0, 3, 4. So your pivot is 4. And then modulo your n is going to be yeah, so your n is going to be 7. Okay, so that's like 7. That looks weird. 7 mod 7 would be 0. I think I'm gonna have to like get back to you on that. I feel like I've missed something. Yeah. So yeah, so like that's for the let's do this. Okay. So the first mid would be 4, right? So yeah, there's so many pointers here that I don't even, yeah. So your first mid is probably 4 from our entire, like from our discussion here. So nums of like nums of 4 is so 1, 2, 3, 4. Yeah, I think like I think if we I think let me sort of write the explanation out a little bit clearer. I'll do this. Yeah, I'll do this offline in the chat. I'm so sorry. It's like super sleep deprivation at this point. I'm very, very sorry about this. So I'll probably like write it out again. Like I'll mention it in like in the channel. Yeah, awesome. Thank you so much for the support, everybody. Yeah, so once all of this, once we get through all of this, we'll probably like we'll hit the because we're doing two different binary searches. At the end, we'll hit whatever we want, and then yeah. Okay. So we'll go through our entire nums, and then we'll get to our target or not, depending on our solution. But I will definitely thank you so much. Oh, I'm so glad that I've like all of you are so like encouraging and welcoming. I'm so happy. Yeah. So I will definitely do like a write up for this, like based on iterations. Yeah, thank you. So like I'll do a write up on that based on iterations, and I'll post it in the chat, or like I'll include it within the repo, so that we can maybe we can like revisit it later or in chat or something like that. So yeah, okay. With this, we've sort of gotten to this, like we sort of solved this problem. There aren't any kind of extra kinds of things to it. It's just like if you see any kinds of chances where thank you so much, Audrey. Like I'm so glad everybody like you folks are amazing. Yeah, so let's get back to our slides right now, and then we'll talk about our next steps and where to go from here. So uh, intersection of two arrays. Okay, so this is like I think like this the next, usually if this is the first time you're attending, usually what we do is we walk through a problem, go through test cases basically, and then we get to the we sort of like discuss where we can go from there. Those are all medium problems what I discuss. Like we're trying to sort of put in easier problems on the channel. We're gonna keep improving on that. And yeah, and I would definitely need to get like a better scratch pad, so I will work on that as well. So this is an easy problem that you can try. So you have two integer arrays, nums1 and nums2, and then you have to return an array of their intersection. Like each element in the result must be unique, and you may return the result in any order. So the input, an example that we put in here is 1 2 2 1 and 2 2, and then you have to return an array of their intersection, right? Seems like this also has to be 2 2. But yeah, you can check more on like the solution in LeetCode. So one more thing was the search and rotated sorted array. It has like another version of it within similar questions. Definitely check that out. And yeah, Sneha, I will definitely get a better explanation in for the second mid that we're finding out. And I'll like put it in the REPL, or I'll like share it in the channel. So I'm very sorry. Should definitely, like Stephanie said, sleep. What is sleep? Yeah. So if you have any more questions on like time complexity related stuff, or if you want to, we could also do this thing where we can work through problems together. So just definitely let me know in the in chat, or like we could discuss on the channel. So is there any other, if you think it's good, we can go to the thumbs up. It's already late. It's super late.
Maybe we can give the audience maybe like a minute or so to type, like to see any questions. Meanwhile, you're catching your breath. You want to drink some water?
Time limit exceeded. Okay. Why is that doing that? That's weird. That did not do it for me. Okay, I will check. I will check once more, and I'll like put it on the REPL as well. Yeah. Oh, that is so awesome. You wake up every morning at 5:30. I mean, like every one of these sessions, I'm so happy. Like Sneha, Joanne, like everybody, any other kinds of questions you have, keep it going. I will, once I catch up on sleep a little bit, I will like post it on, I will post it on the repo or in chat. So
Meanwhile, maybe we can also go to the next couple slides so I can talk about social medias and stuff.
yeah, so
I'll do it. Don't worry. So thank you guys for joining us today. Very exciting to have you. Great participation as usual. If this is the first time you come, feel free to join us on the social media. We're on Twitter, we're on LinkedIn, we're on Instagram. Follow us for the latest update news. And we do have also our next study group section. It will be on reading in 2 weeks from now. We also have a couple events coming up. I believe there's a slide. Go. Okay, there we go. So we have Base and Brew coming up. And we also have the library series. This is the final series. I will be there. We'll be talking about integration between Python and Excel workbook. In case you constantly work with Excel, feel free to come and join us. Also, we will have exciting event about the automating business and financial processes with Liberty Mutual on the 28th. And so feel free to join us, and remember to follow us on Slack, join us on Slack, post your questions. And yes.
Yeah, thank you so much for sticking with us to the end. And thank you for joining.